we are solving video issues for the streaming part, and we are good to go.
Good to go?
Okay. And go, Janos?
Just a second.
No.
We are live. Live. Okay. Okay, we are. Thank you.
Okay, nice.
Another round of applause.
So thanks for having me. I've been to many PyData meetups, and this is a very nice venue, like really nice. And it's also nice to see some familiar faces, like people I've seen on conferences before. So quickly about me, I'm Janos, currently senior AI researcher at appliedAI, a small non-profit company in Germany. And we're doing research, education, and open source software development. I'm mostly working on open source software. If you want to find me on GitHub and Twitter. And yeah, I'm the author and maintainer of optimagic, which I'm going to talk a bit about later. So the plan for today is to use examples from numerical optimization and from optimagic, but I actually want to illustrate some general principles, mostly about interface design. So I think this talk will contain ideas for everyone. And if you're unfamiliar with numerical optimization, it's absolutely not a problem. There's no previous knowledge required. For those who have never seen anything about numerical optimization, this is what it's all about. We have some kind of objective function, typically denoted f of x. We have a guess start parameters, typically called x0. And what we want is we want the argument of the function, so x star, the parameter vector that minimizes the function f. And a very simple example of a function would be this one, the parabola, which is just the sum of the squared parameters. What is optimagic? Optimagic is a Python package for numerical optimization. Most of you have probably used SciPyOptimize at some point. The idea is basically that we are a superset of SciPyOptimize that provides more optimizers, more functionality, and you will see a lot of that later. But we are currently working on really becoming a superset. So if you have code that was written for SciPyOptimize, you don't need to change a single line or anything. It should run. You might miss out on a few features. And optimagic is also NumFocus affiliated, so it's nice to be in that community. But today is, as I said, not so much about numerical optimization. It's about a concept it's called stringly typed and strongly typed. So strongly typed, everyone who has some computer science background has probably heard. Stringly typed, maybe not so much. So what is stringly typed? It's a riff on strongly typed, and it's used to describe an implementation that needlessly relies on strings when programmer or refactor-friendly options are available. That's a bit abstract, so let's look at an example. This might also be your first code snippet that does optimization, so I'll walk you through it. You define an objective function, which is just a function that we saw plotted on the previous slide. And then if you want to run a minimization, either using SciPy or using optimagic, it could look like this. You pass the function that you want to minimize, the initial guess. You select an algorithm. Maybe you configure that algorithm. And maybe you also configure some other things. And what is stringly typed here is the algorithm is a string. It could be something else. Configuring the algorithm relies on strings, dictionary mapping strings to other things. And also the configuration of the error handling here is relying on a string. You might think this is something very specific to optimization, but it's not. Like, let's look at a few other libraries. For example, scikit-learn. Here we have highlighted the scoring argument, which is a string or callable. And that's something that occurs very often in scikit-learn. So if you use something pre-implemented, you typically specify the name using a string. And if you want to do something custom, you can pass a callable instead. Another stringly typed library would be Seaborn, which in fact could be seen as a stringly typed interface on top of matplotlib. And that already suggests maybe that stringly typed interfaces are very popular. And here the main thing that I would consider stringly typed is this scatter KW's argument. So you can pass a dictionary of keyword arguments to the scatter function, even though you are using a more high-level function. So what are advantages of stringly type code? It's considered very beginner-friendly. If you want something, you just write it down. It's very declarative. And it's also easy to implement. For example, when you are wrapping optimizers from another package or any other kind of algorithm, you don't even, at the moment of wrapping, you don't even need to know what options it supports. That's the problem of the user, basically. You just say, here's a dictionary that I will pass to that other function. And it's also convenient when stacking up functionality. We saw that in the scatterplot, regplot example. So if you want to build up functionality but not lose any control over the fine-grained details, then you can also use this pattern of options dictionaries that are passed through. So natural question is, like, is this a good idea then to write code like this? And the rest of the talk is going over problems of stringly typed code and also showing solutions that we chose in optimagic now, but it could also be applied to many other libraries. The first one is a very internal one. Again, this is an example from optimagic. Imagine you want to represent an optimizer history, so the history of all tried parameter vectors and function evaluations as a dictionary of lists. And then that dictionary would be used in several places in your code. So the optimizers will typically write into the history, and the plotting functions will take the history and give you a plot that shows how the optimization went. And now assume you want to rename one of the entries in here. Then really the only thing you can do is search and replace. And you can only hope that you didn't use that word in other places where you don't want to rename it, because there's no other functionality for that. So what would be a better way of doing this? Representing this small history as a data class. It's very easy to write. You import data class. You define the data class that has the same fields as the dictionary had, like keys. And if you now want to rename something and you're using VS Code, for example, you press F2 and you can very safely rename that also in all usages of the history. So that's a very easy win. Don't need to talk about it too much, but if you find this pattern in your existing code, like whether it's a library or just some small data science project, you probably want to go in that direction. And that's always when you have fixed fields. Of course, sometimes you can use dictionaries, but if you have the fixed fields that you're expecting and that need to be present, it might be a better idea to use something else. But there are many more subtle problems. So let's again take the example from the very beginning. We are running a simple optimization and we are configuring the error handling here. Then the user will pass the error handling, which is in that case raise. And somewhere inside of the optimizer library, we will have some kind of if condition that checks, okay, let's say we evaluate the objective function. If an error occurs, we check what's the specified error handling. And depending on that, we either raise the error or we replace the function value with a penalty value. And as you can see, the typos could be on both sides of this. The user can make a typo, and it will be very hard to find. But also the developer can make a typo. In this case, the typo is very obvious, but there are less obvious cases. You will see one in a second. And the only way around this is like, if you rely on strings here, is extensive testing or exhaustive if else. You know, if it was something you didn't expect, then you raise some other error. So what could be a strongly typed solution to this problem? You could, at least internally, replace this error handling variable by an enum. So enum is you simply import the enum class, you subclass it, and you specify all the possible options. And then in your code, you know, like, or your type checker, your IDE, all know what are the possible options. If you do have any typo, it will find that. And then somewhere inside our optimizer library, we will, let's say the user still passes a string. We can convert that string to the enum. And then inside our optimizer code, we will have this if condition compared to the one before. And now if we have a typo on the user side, this will result in an error at runtime, in our case, value error. And if we have a typo on the developer side, it's even found before, so that's much nicer. Like when your editor will like flag it right away. Otherwise, you can run a type checker or anything over it, and you will find that really quickly. But we still have this problem that the typo from the user side detonates at runtime. Like we would ideally like to have that early. Assume you run multiple optimizations, and in the third one you have a typo. It's very annoying if this crashes your code. And here you also have an example of a less obvious typo. So we have two of the letters mixed up, very hard to see, can happen very easily, has happened to me many times. And in this case, then the internal enum is not enough because we need to force the user to also use something safer. How can we do that? In the case of optimagic, we replaced the string, which here would be scipy lbfgsb, it's one of the optimizers, by something that you import, like optimagic.algos.scipy lbfgsb. It's a bit more to type, but it's safer. And like from the implementation side, if you want to do anything like that, you have really many options. It could be an enum, as I showed before. It could be a module that has like constant variables defined. It could be a data class, and in fact, for reasons that you see later, in our case, algos is a data class. But in any case, as long as this is a fixed field data structure, your editor and type checker will find any typo that you might have. And as a free benefit, you get, or the users get, much better autocomplete. So you now don't need to remember the algorithm names anymore. You start typing something that goes in the right direction, and you will get the autocomplete. One problem is that many users still prefer the strings. You can, for example, see that in scikit-learn, where you have the string or callable interface, and basically everyone chooses the strings, just because it's a bit less to type. But we're trying to like make the other options like as convenient and fun as possible. So in the hope that people will use it, I show a more advanced example of that later. And now let's come to the next problem, and that's the question like if I have this stringly typed pattern of an options dictionary, my question is like what can I put there? So in my case, I selected a scipy lbfgsb optimizer, but how did I know that I can put stopping max iter, and what else could I put there, and what are the valid values? So if I want to do that in scipy, which has a really good documentation, by the way, I would have to go to the documentation. I see options, okay, all optimizers support this. Then for my particular optimizer, I need to click here. Then I go here to the one I selected, and I will finally see, okay, it has these additional options, and I can select one. And let's assume I want to save some memory, so after reading this, I decide that I want to use this max core option and want to set it to a lower number. So I go back, I type this into my dictionary, and like this was already cumbersome enough, but it's very easy to make a typo. In fact, I made one here, I added another R, which would also be a sensible abbreviation. And actually, I think if you do this, so last time I checked, nothing happened, but I had a SciPy maintainer in the talk when I gave it, so I think they fixed it by now. So at least you should get a warning that like you have an unsupported option. But it's still something that detonates very late at runtime. So what are potentially better options for doing that? And this is, again, not super specific to optimization. It happens everywhere where you select some algorithm. We could have configured algorithm objects. So in that case, like you already previously saw, you can do om.algos.something. And that something could be a class of which you can create an instance. And then when you do that, you get all the standard tools that your IDE and editor have. So you can hover over it, you find all the valid options. And by the way, in optimagic, we don't just do like int or float. We say it's a positive int, non-negative int, and so on. And then the more you type, for example, you start typing mutation variant, hit autocomplete, this always zooms in and shows you all the relevant options, and it becomes really easy to configure an algorithm, and you don't need to go to the documentation at all. So after you've used this for even 10 minutes, if you're used to doing a lot of optimization, you will miss it in other places. There's an extra bonus. First of all, the algorithms can now validate the options before the optimization runs. So you can get, if you still make a mistake, you can get the error very early. And also, like you can add a few extra things to this algorithm classes, like copy constructors that make it possible to construct modified copies out of a base algorithm that you might specify. For example, here we use a trust region optimizer, configure it with basic options, and then we try out multiple different initial radii to see which one works best. And that's like if you consider that you have an options dictionary and you forget to make a copy, you can very easily run 3 times the same optimization without even knowing. So that was very static, and now I'll try to show you one live demo. I hope it works, of a bit more advanced options. And I will have to go give you a bit of background on one specific task that comes up with optimization, which is selecting the algorithm. We always just saw, okay, you select one, but how did we come up with that? If you're not interested in optimization, you can focus on the later part. So selecting an algorithm for optimization is actually super important. Like it can make all the difference between you run your code for a day but don't solve your problem, or you solve your problem in a few minutes or maybe even seconds. So it's really important, but it's also really hard. Is this large enough? Or I'll try to make it more larger. Okay, maybe better. For selecting an algorithm, you have basically 3 steps. The first one is, we call it theory. It's not very theoretic, but this is based on the properties of the problem you are solving. So it cannot be still too small. Okay. Basically, what you need to do is you need to answer a bunch of questions of the problem you have. It's not really based on the theory of optimizers. It's really looking up in a decision tree that you see here. The second step is experiments. So you select like 2, 3, 4 candidate algorithms. You run them. You compare whether they work or which one works best. And then you finally run the optimization. And we have, for example, in the documentation, this simplified decision tree that can you help if you're an absolute beginner. You basically just answer 3 problems. Do you have nonlinear constraints? You typically know that. Is your function differentiable? Maybe you know that. If not, check, like, are there many if conditions? Then it's probably not differentiable. Is there noise? It's not differentiable. Otherwise, it is. Can you exploit a least squares structure? And based on these 3 questions, you then get like 3 optimizers that you can try out. But of course, for this, you would have to go to the documentation. So you have your code open and you have the documentation open. And we just talked about that this is actually not so nice. So what can you do? You import optimagic SOM, as always. And then we implemented what we call filtered autocomplete. So you already know this om.algos, which gives you, for example, access to all the algorithms. But you can now also filter them. For example, you could say you have a scalar problem. You have maybe nonlinear constraints. And you want a gradient-free algorithm. And then you only get the ones suggested that you that are still like available, that satisfy all these criteria. And at any moment you can type .all, which will give you a list of all the algorithms that you can choose from. Or you can choose .available. So optimagic has many optional dependencies. So this would then only limit the ones that you have currently installed and could choose from. And also, of course, like if you at some point want to select an algorithm, let's choose LBFGSB. You type brackets, you get all the options that you can choose from, and you can configure it very easily. Yep. Now let's look at one example problem. So you have done that once. This is the trit function. It's a very simple, differentiable, very well-behaved optimization problem that only has one global optimum. There are no local optima or anything that could trip up the optimizer. And since it's differentiable, we can also define a gradient. So let's go through this decision tree for that. No, we have no nonlinear constraints. We have no least square structure. It is differentiable. You get these three optimizers you can compare. If you want to use the autocomplete instead, like this is a very simplified thing and limited to very few optimizers. You can also do that. So om.algos.scalar, gradient-based, local, and available. Looks good. And then if you're actually using this, we suggest you copy-paste this list because if you update optimagic, we might have added more optimizers so you don't get the same list. So then you could do candidates equals this list. And let's maybe remove a few so we don't have so many. But you could actually also run all of them without a problem. So candidates is defined. Step 2, experiment. You loop over your algorithms and you run a minimization with all of them. Now, to save time, you limit to a very small number of function evaluations or iterations. Otherwise, of course, like it could take really long, not in this case, but in general. And then you can look at a plot that simply compares all of them. This is created using Plotly, so if you want to select lines or like disable lines, you can do that. And then we could find out like what is the most promising one or the two most promising one. And that one we would run until completion. Then we can look at it. We had all these like attempts that we started for a few iterations. Actually, the stopping criteria are not the same for all, so some run a bit longer, no problem. But you see that then, okay, finalizing, starting from the best value of the experiments, we actually do get a bit further than what we had in the beginning. And in some cases, this can really make a huge difference. And this is, as I said, a super simple optimization problem. There's no local optima. But let's try a few algorithms that we would not recommend. Like if you answer a question, you would never select them. And this is, for example, the Nelder-Mead algorithm, which is a gradient-free algorithm that you would not use for this differentiable function, especially if you have a closed form derivative, and the Kobila algorithm. And if we run those, we can actually see that it was important. Like the one that we wanted, it solves the problem super, super fast. The Kabila algorithm at least solves the problem after a lot of time. This narrow-meet algorithm, which is a good algorithm for other problems, doesn't solve the problem at all. So it can't get stuck in a local optimum because there is none, but it gets stuck somewhere. And to make things worse, it doesn't even know that it got stuck. So it thinks it converged successfully. So if you have important applications of optimization, you always want to check multiple optimizers against each other, and optimagic makes that very easy. To wrap things up, if you want to read more on this topic of like how could you change your code or a library that you're working on to use these concepts and make the library more user-friendly, before we made the changes, we wrote up a detailed enhancement proposal that like explains why we do this and what we want to do. And this has also all the other resources listed in the beginning. But I want to highlight two of them. That's a blog post called Writing Python Like It's Rust. If you only have 20 minutes and don't want to read anything else on that, read that blog post carefully. It's really, really good. It is what got me started on this topic. And if you have more time, or maybe you're a beginner and still learning about Python, then read Robust Python. It's also a really good book that like gives you many examples for these concepts and really helps you to find the right data structures for what you're doing. Lastly, if you want to get involved with optimagic, if you're using optimization and you have a favorite optimizer that we don't have yet, please suggest it. Otherwise, we also have a list of ones we want to wrap but didn't have the time yet. So if you want to do that, it's really easy. You can get started in an hour or so. Like we can help you with the first one, and then you can do more. Provide feedback about anything that's missing, or share the word about optimagic and like us on GitHub. Thanks a lot.
So, thanks a lot. That was great. So we have some time for a few questions. Who wants to ask the first question? Who is brave enough to go ahead? I had one, but I forgot about it. Okay. Oh, I can ask. So you mentioned the fact that you had an enhancement proposal before adding this to the library. And how was the migration to this thing in terms of user and breakage or how did it work?
So we do enhancement proposals for everything that has deprecations or breaking changes, which we have a few, mostly very mild deprecations. So to be honest, I started alone writing it up, but then got like a lot of feedback from the core contributors. And in the end, we had a short presentation for active users that we know and got a lot of feedback, and all of them really changed the proposal and made it better. Yeah.
Thank you. Who else has a question? Go ahead, Luca.
Ciao. Could you, excellent talk, I especially like the fact that you replaced the strings with objects, but I was a bit more curious about how you implemented that. So all this filtering, chaining of objects, what kind of objects are those? And in the end, why did you choose to keep them capitalized?
So yeah, you're talking about the filtered autocomplete.
Yes.
First question: what kind of objects are these? They are data classes, immutable data classes with properties.
Okay.
And we chose data class because you need something that supports type hints really well. We wanted it to be immutable, so it was just very, very easy to do. And about the naming convention, we talked a lot about that, and I'm still not sure what would be the right way to do it. we had a naming convention of lowercase with underscores for algorithms. So we wanted to somehow separate what are the algorithms that you can select and what are these additional data classes that are just more filtered. We wanted some visual distinction. It would probably be more intuitive to have it the other way around, but given the path dependency, this is what we chose.
And so every data class property contains a string representation of the path where the object, like the algorithm, lies.
It contains the actual class.
Okay.
And you probably suspect that this would be a nightmare to maintain because you have all these. Yeah, we auto-generate this. So we have a pre-commit hook that goes over, like, discovers all the use import lib to discover all the algorithms, and all the algorithms are decorated, so they have some metadata that helps us to classify is gradient based or not. And then we auto-generate the code. It's super simple, like 400 lines of code to generate. Like the generation code is like 400 lines. The generated code is 4,000 or so, and super hard to read. Like, it would be impossible. We have like 7 different filters, and you can do any order. So it would be a nightmare to maintain.
Wow. Clever.
Other questions from the audience? Yes.
Thank you for your presentation. How did you test your code in order to make it work correctly?
How do we test our? Okay, that's actually a long answer. Like, for all the code that implements the actual functionality of optimagic, we have very fine-grained unit tests. We use a mostly functional programming style, even though now we use some classes, but they're mostly immutable. So it's really easy to test everything in isolation. And then for the algorithms that we wrap, we make some sanity checks. So all of them have to solve at least a very simple problem. And we also periodically benchmark them, but that's a lot of computation, so we cannot do that as part of our CI. Yeah. And this specific code for the filtered autocomplete, we test both the generation code and the generated code to make sure that this works.
Okay, thank you.
We might have time for one last question. If not, let's thanks again, Janos. And do we need a small break for the video to change, or?